welcome to the system. When night falls, the house grows quiet. The lights go out, the TV falls silent, the phone lies motionless on the table. You might think the day has come to an end, but for the digital systems inside the house, night is just another work shift. Even when the phone screen is off, it can connect to servers, it checks messages, it backs up photos, it updates apps, it refreshes location data, the TV searches for new software, the smartwatch syncs health data, a camera sends status information to a remote service, the router keeps connections open. Even when you're not doing anything, your devices keep communicating. At first glance, there's nothing unusual about this. Modern devices must communicate to provide services. Data transfer is required for a message to arrive, the weather to be updated, or files to be backed up. But the unspoken question is this: which device is communicating with whom, when, and why? Most people know how many devices they have at home: a phone, computer, TV, tablet, game console, printer, camera, or smart plug. But they don't know how many connections these devices establish, because what's visible is the device. What's invisible is the network. A network isn't just wireless internet. It's a communication space that connects every device in your home to one another and to the outside world. Within this space, every device has an identity, an address, and a behavior pattern. Some only communicate when you're using them. Some establish connections in the background throughout the day. Others reach servers you've never even heard of. A turned-off screen doesn't mean silence. Just because an app isn't visible doesn't mean it isn't running. Just because a device isn't being used doesn't mean it isn't generating data. When a systems architect looks at a home, they don't just see the devices, they see the flow. Which devices are connected to the network, which one is constantly sending data, which one becomes active during the night, which one keeps connecting to the same server over and over, which one actually needs the internet. These questions don't stem from paranoia, they stem from the need for control, because to control a system, you first need to know its boundaries. The boundary of a home network isn't defined by walls, it's defined by the router. Devices inside pass through this point to go outside. Responses coming from outside also enter through the same point. That's why a router isn't just a small box that distributes the internet. It's the hub of your home's digital traffic. But most people never pay attention to this hub. As long as the device is working, they assume the system is healthy. If there's internet, there's no problem. If a video plays, the connection is good. If a message goes through, everything is normal. Yet, a system that's working isn't necessarily a system that's working correctly. While a device is performing its function, it may also be sending unnecessary data at the same time. An app may be sharing information with analytics companies while providing its main service. A TV may be recording viewing habits while displaying content. A game may be transmitting much more than just gameplay data. This doesn't mean every connection is harmful, but it also doesn't mean every connection is necessary. An architect doesn't make judgments first. First, they draw the map. You can't manage traffic in a city without seeing the roads. You can't establish security on a network without seeing the connections. Without knowing which device is going where, you can't decide what to block. That's why the first step isn't to block. The first step is to make things visible. When you start observing your digital life at home, you'll encounter a surprising reality. The devices that seem the quietest are sometimes the ones that talk the most. A TV you're not using, an app you thought you'd closed, or an old phone forgotten in the corner may still be active on the network. Systems operate based on rules, not intent. Even if you forget about a device, it continues to carry out the task assigned to it. It checks for updates, it connects to its server, it refreshes its time information, it sends telemetry, it keeps its connection active. When people stop, the system doesn't. Understanding this isn't about developing a fear of technology. On the contrary, it's about truly seeing technology for the first time, because control isn't about cutting off every connection. It's about knowing why each connection was established. The house may be quiet, but the network never truly sleeps. To read a network's invisible map, you first need to understand how devices communicate. No connection on the internet is directionless. Data originates from somewhere, travels to a specific address, and waits for a response. Every device in your home carries an identity within the network. The router assigns it a local IP address. This address indicates the device's location on the home network. A phone, computer, and TV may all be connected to the same network, but each is identified by a different address. Just as every building in a city has an address, every device on a network has an address, but the IP address doesn't tell the whole story. There's another identifier tied to the device's network cards. This is called the MAC address. Routers often distinguish devices using this address. When you see an unfamiliar device on your screen, the sequence of letters and numbers you see might be its signature on the network. However, knowing the device's identity doesn't mean you know who it's communicating with. When you open an app, you interact with it using a recognizable name. You type in a website's name or tap the app's icon. The network, however, operates using addresses, not names. This is where DNS comes into play. DNS is an invisible guide that translates names on the internet into technical addresses. When you request a domain name, your device first asks which server that name belongs to. Once the address is determined, a connection is established. The user only sees the page loading. But behind the scenes, a query has been sent, an address has been found, and a data connection has been established. Consider a single weather app. You might think the app is connecting only to a server that provides weather information. In reality, it can simultaneously access a location service, an analytics platform, an ad network, an error reporting system, and a notification service. You see a single action on the screen. On the network, however, multiple doors open. Not every door serves the same purpose. One connection is necessary for the app to function. Another measures performance. Yet another analyzes usage behavior. Another verifies the ad ID. Some are set up for security. Some generate commercial data. For this reason, evaluating data traffic simply as present or absent is insufficient. The architect classifies connections, the necessary ones, supporting ones, monitoring ones, unknown ones, those posing a risk. Blocking without this classification can disrupt the system. You might block a domain name and the application stops working. You might assume a service is unnecessary, but the login process depends on it. Control isn't about building a random wall, it's about understanding the connection's purpose. Data is transported in packets across the network. Large content is broken down into small segments, delivered to the destination, and reassembled on the other end. When you watch a video, you see a single stream. In reality, thousands of data packets reach your device. The system organizes all the pieces without you even noticing. The router tracks which device each packet belongs to. It ensures that responses reach the correct device, even when your phone, TV, and computer are all using the same connection. That's why a router isn't just a gateway, it's also a manager. However, most standard routers don't show the detailed story behind the traffic. You can see the connected devices and the amount of data, but you can't always see which domain names they're accessing or at what times they're active. A message arrives, a video opens, the decisions in between remain invisible. Some of these decisions are made by the device, others are defined by the app developer. You simply tap the final button. That's why digital control extends beyond the permissions on the screen. Disabling an app's camera permission is important, but knowing which servers it connects to is another layer entirely. Permissions manage the doors inside the device. Network rules manage the paths leading to the outside world. The true picture emerges when these two layers are viewed together. What is being accessed inside the device? Where is it connecting to over the network? When is the connection established? How often does it repeat? For the architect, it's not a single connection that matters, but the behavior pattern. If a device reaches the same server at the same time every night, that's a routine. If it suddenly connects to an unknown address, that's a change. You can't detect abnormal behavior without knowing the normal behavior. That's why security begins not with blocking, but with defining the baseline. The voice of a system isn't found in a single packet, but in its repetitions. Once you start reading the map, the internet ceases to be an invisible void. It transforms into a living structure with paths, addresses, and behaviors. The question is no longer whether this connection exists, or why does this connection exist? Simply seeing the map isn't enough. Once a system becomes visible, the next question is, where is this structure's control point? In a home network, the first control point is the router. This is because all devices usually pass through it to access the outside world. Therefore, the first step is not to set up a new device, but to understand the existing network. When you open the router's interface, you'll see a list of connected devices. Some are clearly identifiable. You'll see the names of your phone, computer, or TV. Others, however, are listed only by the manufacturer's name, IP address, or a meaningless device label. Not every device you don't recognize is dangerous, but no device you don't recognize should go unchecked. An architect starts by taking inventory. How many devices are connected? Which ones belong to you? Which ones belong to family members? Which ones haven't been used in a long time? Which ones are active only at certain times? Which ones actually need internet access? A firewall set up without answering these questions is merely a guess. The second step is to separate the networks. Your phone, work computer, guests' devices, and smart home products do not all require the same level of security. It is not always necessary for a light bulb or a TV to be on the same network as your personal computer. That's why many routers offer the option to create a guest network. A guest network isn't just for guests. It can also be used to separate devices you trust less from your main network. A device can access the internet but may not be able to directly connect to other devices in your home. This way, an issue with a single device won't affect the entire network. The third step is to change the default settings. The router's admin password, the Wi-Fi network password, and the factory settings of smart devices are all part of your security perimeter. If you leave the default password unchanged, the system's door may appear locked, but everyone knows where the key is. A strong password alone does not guarantee perfect security. However, a weak password can render all other precautions meaningless. The fourth step is monitoring. You should check how much data a device uses, at what times it is active, and which domain names it attempts to access. Not every router displays this in detail. This is where DNS logs, NextDNS, Pi-hole, or network monitoring tools can come into play. But the tool is not the goal. The goal is to make invisible connections readable. When you see that a TV accesses the same domain hundreds of times a day, you no longer have an assumption. You have an observation. You begin to see the difference between the server required for an app to function and an ad network. Then you classify them. Essential connections are preserved, suspicious connections are monitored, unnecessary connections are filtered out, unknown connections are investigated. Blocking everything at once is not the right approach, because a strict rule system may silence the noise, but it prevents you from understanding what it's disrupting. An architect makes changes in small steps, add a rule, observe the system, record the result, revert if necessary. Control isn't about imposing random restrictions. It's about understanding the outcome of a change. Network security isn't a one-time task either. A new phone gets connected, a new app is installed, the TV gets updated, a service changes its address, maps are constantly updated. That's why the real power lies not in having a perfect list, but in establishing a system that can detect changes. You don't have to figure out all the traffic in your home today. Open your router's interface, check the connected devices, make a note of any unfamiliar names, remove devices you don't use, change the default passwords. If possible, set up a guest network, then just observe. What you see on the first day might seem meaningless to you. But as patterns begin to emerge, your network's behavior becomes clearer. If you know when a device is communicating, you can also understand when it needs to be silenced. If you know why a connection is being established, you can make a conscious decision about whether to allow it or not. This is where the difference between a user and an operator becomes clear. A user is satisfied when the system works. An operator knows how the system works. The walls of your home protect your physical space. Network rules, on the other hand, define the boundaries of your digital space. If you don't set those boundaries yourself, devices, apps, and external services will set them for you. I'm an architect. We'll meet again in the next recording. When that day comes, you'll understand why these recordings exist. System status, active. Protocol, CO complete. Next protocol, Z15, status, running.